Hello, Year 12. I've made this short video for you in order to help you understand why we get interference patterns um, when we have two slits and a light source, coherent light source illuminating them. We're going to be looking at this um, with consideration of the path difference from each wave. So to begin with, what we have on the screen, we've got the black rectangle to the right-hand side. That's the screen the light's going to illuminate. We have the double slits, and we also have a laser source. When the laser source is switched on, it is going to pass through the two double slits where the light diffracts. It spreads out, the wave fronts spread out, and we have an area where the two diffracted wave front sets are going to cross over and interfere with each other. Why do we get these different fringes? First of all, we're going to have a look at the central bright fringe. If we consider the rays that are coming from each of the slits, we can see that they're both traveling the same distance. If this light is in phase, then we can see that, for example, they both leave as peaks and they arrive and travel the same distance at that screen, then they're both arriving as troughs. So if we have a trough and a trough, we're going to have a super trough, and that's constructive interference. If we were to go forward a cycle or so of the wave, or not a whole cycle, but half cycle, then we're going to have two peaks meeting. Because these rays travel the same distance, there is no path difference. We therefore get constructive interference at the point they meet. Right, so that's the first central bright fringe. But what about the other bright fringes? So at the other bright fringes, the rays are actually traveling different distances. So in this case, it's a slightly different rule. If we consider the far fringe, we can see that at the top we've got 4 wavelengths distance, and on the other diagonal ray it's about 5 wavelengths long. So both rays have a path difference of 1 wavelength this time. They're traveling different distances. Just to mark in the waves, what we see now is that despite the fact they're traveling different distances, because one of them is exactly 1 wavelength longer, we still get two peaks meeting at the screen. Therefore, we get constructive interference. In fact, this is our general rule. If the path difference is 0, 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, a whole number of wavelengths, we are going to get constructive interference. Okay, so what happens at dark fringes in that case? At dark fringes, we still have the same situation where our coherent light source is illuminating the double slits, light is diffracting, we're getting an interference pattern where the two sets of wavefronts cross over. At a dark fringe, the two rays still travel a different distance to reach the dark fringe. However, the wavelength or the length of each path now is slightly different. So I've got 4 wavelengths and 4.5 wavelengths. Therefore, our path difference is now 0.5 wavelength. If we mark on the rays, we can see it at the screen now. If the light is in phase to begin with, then we're going to have a trough and a peak meeting at the screen. Therefore, we get destructive interference. This is our general rule for the dark fringes. If our path difference is an odd number of half wavelengths, then we get destructive interference. So, to summarize, if we're using coherent light that is in phase, our path difference is a multiple of a whole wavelength, then we get constructive interference. On the other hand, if our path difference is an odd number of half wavelengths, we get destructive interference. We would still get an interference pattern if light is not in phase, provided the phase difference is constant. What will happen is that the interference pattern will be shifted left or right, however. You could have a think about the path differences to figure out why.